Okay, so I think we can start. So today we will have Ivan. So Ivan is a phenomenologist that did the PhD in Barcelona and then a postdoc in Ohio State and now is back in Spain in the Basque country. So he will talk about the neutron star wind and the potential of these sources for an MeV astrophysical neutrino flux.
Yeah, thank you very much for the introduction, Marta, and thanks a lot for the invitation. It is a real pleasure to talk here in front of this diverse audience. So yes, I am Ivan Esteban. I am an assistant professor at the University of the Basque Country, and throughout this seminar, I'll try to convince you that accreting neutron stars in what in the literature is known as common envelope systems have the potential to be the third MeV astrophysical neutrino source. So this is work that I carried out in collaboration with Joachim Kopp, you can see him here on the right, and John Beacom, you can see him here on the left. Now, before beginning, I wanted to start with a quote by John Bacall from more than 30 years ago, which says that neutrino astronomy is interesting for the same reason it is difficult. And indeed, neutrino astronomy, that is detecting neutrinos from extraterrestrial sources, is an extremely challenging endeavor because neutrinos have tiny cross-sections, and hence to detect them, we have to build massive detectors with very low backgrounds. However, precisely because of their weak interactions, neutrinos and astrophysical neutrinos, after being produced typically deep inside astrophysical sources, they exit the sources basically without interaction, and then they travel essentially at the speed of light until they reach the Earth, again, basically without interacting in the environment, on their way to the Earth. So this means that detecting neutrinos from extraterrestrial sources provides us with direct observational evidence of what is going on deep inside astrophysical sources. This is very different from the standard photon astronomy. So if you look at the sun with your eyes, you are not seeing the photons that are being produced right now at the core of the sun because of nuclear fusion reactions. Instead, what we see is the result of those photons scattering inside the sun for hundreds of thousands of years and getting their energy degraded by a factor of about 1000 until they can finally escape and reach the Earth. And even though propagation effects between the source and the detector are not super important for solar light, they are important for other light sources. So one example is that there's many more stars in the Milky Way than what we can see with our naked eye during the night, and partly that is because interstellar dust absorbs their light. So neutrinos don't have these problems. Detecting neutrinos from extraterrestrial sources, detecting astrophysical neutrinos provides us with real-time information of what is going on deep inside sources without significant propagation effects. Now, I am not an astrophysicist, I'm a particle physicist, and so from the particle physics point of view, astrophysical neutrinos are also extremely interesting for many reasons. To begin with, neutrinos only interact weakly. And so precisely characterizing the properties of neutrinos, including astrophysical neutrinos, is a relatively clean window to characterize potential new weaker than weak interactions. On top of that, since astrophysical neutrinos travel extremely long distances before being detected in principle without interaction, precisely characterizing the properties is a great way of probing potential new effects that only show up after traveling for very long distances. Some example effects that I have in mind include neutrino decay or potential Lorentz violating interactions that only show up after traveling for very long distances. As another example, astrophysical neutrinos are typically born in large density, high temperature environments. And so again, characterizing the properties of astrophysical neutrinos is a great way of learning what are the laws of particle physics in high density, high temperature environments. Now, despite the usefulness of neutrino astronomy both for astrophysics and for particle physics, we know about very few astrophysical neutrino sources, and that's because they are very hard to detect. And so we know for sure that the sun emits neutrinos. This is a picture of the sun. And down here, this is a picture of the core of the sun. So not of the sun, but of the core of the sun, taken in neutrinos by the superchemical collaboration. We also know that core collapse supernovae, that is massive stars that run out of nuclear fuel and collapse under their own gravity, emit neutrinos. And we know it because we detected them more than 35 years ago. And in the last decade or so, there has been growing evidence that active galactic nuclei are also a source of astrophysical neutrinos, because the ESCAPE experiment has evidence for active galactic nuclei emitting high energy neutrinos, and also more recently, they have provided evidence for the plane of our own Milky Way emitting high energy neutrinos. So here, solar and supernova neutrinos have MeV energies, and neutrinos detected by IceCube have ordered TeV energies. And so despite having only essentially 3 classes of sources, we have learned a lot of astrophysics from them. So we now have direct observational evidence for the nuclear fusion reaction chains that fuel our sun, thanks to observing the neutrinos. On top of that, we can now use solar neutrino data to determine the properties of the sun, including its chemical composition that can be otherwise pretty hard to determine. We also have direct observational evidence for the origin of type 2 supernovae, because we observed neutrinos from supernova 1987A, and this also provides us with direct observational evidence of what we think is the main way in which astrophysical neutron stars and black holes get formed. And finally, detecting astrophysical neutrinos from active galactic nuclei in IceCube has provided us with a direct window into the astrophysical environments that can accelerate cosmic rays to extremely high energies, to TeV energies, thus shedding light on the 100-year-old problem of the origin of cosmic rays. And again, all these astrophysical achievements are possible with few sources because astrophysical neutrinos provide us with clean, real-time information of what is going on deep inside sources. Again, I am not an astrophysicist, I'm a particle physicist, and from the particle physics point of view, the study of astrophysical neutrinos has been extremely fruitful. Here are just some examples that I wanted to highlight. There's many more, but for instance, our first laboratory evidence for physics beyond the standard model, which is neutrinos having a non-zero mass, originally came from the study of solar neutrinos. And this was worth a Nobel Prize in physics 9 years ago, before AI took over the Nobel Prizes. So now, talking seriously, determining the properties of astrophysical neutrinos is a window into particle physics in general. So one example is neutrino masses and solar neutrinos. Another example, also coming from solar neutrinos, is this plot here. So this plot shows the solar electron neutrino survival probability. So this is the probability for an electron neutrino to stay an electron neutrino after it exits the sun and reaches the Earth as a function of neutrino energy. In the standard scenario, when there is just neutrino masses and mixing, then the probability takes this dark blue shape. But if there are additional stellar neutrinos, the shape looks more like the green curve. And if there are new interactions between neutrinos and matter, since the matter inside the sun is so dense, this can modify the neutrino transition probability to the pink line or to the yellow line. And so as you see, precisely characterizing the energy dependence of this neutrino survival probability allows us to pinpoint the particle properties of neutrinos. Another example, these are limits that exist on the neutrino lifetime. And as you see, the main direct observational limits come from supernova 1987A, IceCube, and solar neutrinos. And the idea is very simple. Before reaching the Earth, these neutrinos traveled extremely long distances. And so the fact that we observe them means that they cannot decay. And so this simple argument sets what are the leading direct observational constraints on the neutrino lifetimes. And so, again, there are many more examples, but in general, neutrino astronomy is very interesting for the particle physicist, I think, because neutrinos in general are clean probes of new interactions, and astrophysical neutrinos are clean probes of dense matter effects and potential propagation effects. Now, because of the interest of neutrino astronomy for particle physics and for astrophysics, we would like to get as many astrophysical neutrino sources as possible. And so for the rest of the talk, I will discuss one particular astrophysical environment, which is called common envelope evolution. So in case you haven't heard about it before, common envelope is a system or an evolutionary phase in which two stellar cores share a common envelope. The way in which this happens is shown in this cartoon here on the left, and the idea is very simple. So you start with two different stars that form a binary system, and then there is either an external perturber, so a nearby star passes by and perturbs the system, that makes the two stars fall onto each other, or one of the stars exits the main sequence, and so it becomes a giant star, it blows up in size, and it swallows the other star. Now, when this happens, the two stars will share a common envelope, and instead of just orbiting each other in regular orbits, they will start spiraling into each other. This is because in the envelope, the densities are relatively large for astrophysical standards. And so there will be a lot of friction, a lot of drag onto this core that was captured, and so it will in-spiral because of this friction onto the original core. Now, this process ends either when the two cores merge, or when, because of this friction, the envelope is heated so much that it gets expelled. If it gets expelled, then you end up with two cores very closely orbiting each other. Now, if this is the first time that you hear about common envelope evolution, it may sound extremely exotic to you, but indeed it has been relatively well known in the astrophysics literature since the 70s, more or less, and it is thought to be necessary to explain the origin of many tightly bound binary systems. That is, binary systems in which the distance between the companions is very small. And this is because this process of friction, this process of drag, is a very efficient process to reduce the orbital separation among two stellar cores. So examples of such systems that we think require common envelope to be formed include type 1a supernovae, which are systems in which either two white dwarfs merge or a white dwarf is accreting from a nearby star, X-ray binaries, so systems in which neutron stars or black holes accrete from nearby stars, and the recently discovered gravitational wave sources in which two neutron stars or two black holes merge. Now, the reason why we think that we need common envelope evolution to explain gravitational wave sources is pretty simple to understand, so I'll explain it in a little bit more detail. The idea is very simple. If you have two neutron stars or two astrophysical mass black holes, and you want them to merge within the edge of the universe, gravitational wave emission is a very inefficient process, so to begin with, they should be within one astronomical unit of each other. Otherwise, if they are farther away from each other than one astronomical unit, then gravitational wave emission is very inefficient, and there is no way that they can merge within the edge of the universe. Now, we know that before being neutron stars and black holes, these objects were giant stars. Funnily enough, we know it partly because we observed neutrinos from 87A. So, before being neutron stars or black holes, these objects were giant stars whose size is much more than one astronomical unit. And so the fact that these objects have to be within one astronomical unit of each other to merge by emitting gravitational waves, and that in their evolutionary past they were bigger than one astronomical unit, naturally implies that at some point in their evolutionary past, they were sharing a common envelope. So this is just one example argument. There's many more. I don't want to get into the astrophysical details, but this is just a cartoon from a review paper by Ivan and collaborators. And again, I don't want to get into the details, but this plot shows how starting from two main sequence stars, you may end up with a type 1a supernova, with an X-ray binary, or with two neutron stars merging with each other. And all these formation pathways involve at one point or another common envelope evolution. Again, because sharing a common envelope is an extremely efficient way to reduce the orbital separation. Now, despite the importance in astrophysics, it is still unobserved and ambiguously. So people claim some signals, but they are always ambiguous, and you can understand why. In common envelope, all the action is happening inside the envelope. So all the electromagnetic signals are being shielded by the envelope. On top of that, this process is also extremely challenging to simulate. So we know very little about it, and the reason why it's very challenging to simulate can be understood on simple grounds. If you imagine common envelope with a neutron star, so the size of a neutron star is of order 10 kilometers, and the size of the envelope of the giant star that is swallowing it is more than one astronomical unit. So there is a huge separation of scales here that makes the problem extremely challenging computationally. And so we definitely need new signatures of this process to learn more about it. So for the rest of the talk, I will focus on one particular case of common envelope systems, which are common envelope systems involving neutron stars. So this is a neutron star that is being swallowed by a giant star. Again, understanding this process is important to understand the origin of X-ray binaries, which are neutron stars or black holes accreting from nearby stars, and also to understand the origin of gravitational wave sources. So what happens when a neutron star is swallowed by a giant star? There's mainly two processes. First of all, because of the large ambient density in the envelope of the giant star, the neutron star will in-spiral onto the companion because of this friction, because of this drag. And while it's doing this, the neutron star will accrete material because of the large ambient density. And so one can estimate on simple grounds the rate at which the neutron star will accrete material. And one can do simple accretion theory. So the idea conceptually here is very simple. You can sit on the rest frame of the neutron star. And so in this rest frame, there will be some wind of plasma from the envelope of the giant star flowing towards you. And you can estimate which fraction of that plasma has a negative total energy, that is, it is gravitationally bound to the neutron star. And that material will eventually get captured by the neutron star. This very simple estimation gives an accretion rate that is proportional. So the accretion rate is usually called m dot. And this is mass per unit time that falls onto the neutron star. And this accretion rate in this simple picture is proportional to Newton's constant squared, to the neutron star mass squared, and to the ambient density rho. So the larger the ambient density, the faster you will accrete. It is also suppressed by the velocity v at which the neutron star is moving inside the envelope. And intuitively, that's because if the neutron star moves extremely fast, then it will be very hard to gravitationally capture material. And on top of that, there's another effect. So the envelope of the star is not a gas of collisionless particles. It's a plasma in thermal equilibrium that has pressure, and this pressure will also hold accretion. And technically, this suppresses the accretion rate by the power of the speed of sound, CS, of the medium. So if we take this simple order of magnitude estimation, and we plug in typical numbers for common envelope events, we get that the accretion rate onto the neutron star in common envelope systems should be of the order of 10 to the 2 solar masses per year. Now, this number is already impressive, but if I put it in the international system of units, it's even more impressive. This is 10 to the 25 kilograms per second. This is a huge accretion rate. And so, as you can imagine, this huge accretion rate will drastically modify the physics of accretion. So, indeed, typically accretion in astrophysics is limited because of two effects. So, first of all, when material falls onto the neutron star, the inflow gains kinetic energy, it gets accelerated by the gravitational field of the neutron star. And hence, this kinetic energy gets converted into heat, the material heats up, and it starts emitting radiation, it starts emitting light. Now, if the temperature is high enough, this light will exert pressure on the material that is falling in, and this pressure can at some point compensate gravity and halt accretion. On top of that, at least in equilibrium, as material falls onto the neutron star, it gets kinetic energy, it gets heated up, and so, at least in equilibrium, this kinetic energy has to go somewhere. Typically, the most efficient way in which energy is dissipated is precisely by emitting radiation. And so, both the combination of radiation pressure and the fact that the rate at which you are able to dissipate energy limits the rate at which in equilibrium you can gain energy, combine together to set a limit on the accretion rate that is usually called the Eddington limit, and that for a neutron star is of the order of 10 to the minus 8 solar masses per year. So if you go back to the number that I quoted before, this is 10 orders of magnitude stronger than the Eddington limit. So is it possible to violate the Eddington limit by 10 orders of magnitude? Well, indeed it is, and the basic physics has been known since the 90s. So the first idea is very simple. So how do you avoid radiation pressure from halting further accretion? Well, again, the idea is very simple. So here in this cartoon, I show how material falls onto the neutron star. The neutron star is orbiting the envelope of the giant star. And so when material falls, it gets hot, and then it starts emitting radiation. Now, the material here is so dense that light does not travel in a straight line at the speed of light. Instead, light diffuses inside the material. Now, if the inflow velocity is large enough so as to be larger than the velocity at which light can diffuse outwards, then the hot parts of the accretion flow will not be able to efficiently exert pressure on the outermost layers. intuitively, if we consider here some fluid volume element that is sinking onto a neutron star that has a hot a hot bottom part and a cold top part, the hot part will start emitting radiation that will in principle exert pressure on the cold part. But if this fluid element is sinking so fast, then by the time that this radiation has reached the supposedly cold part, the fluid element has already sunk deep inside the neutron star. This means that if the inflow velocity is large enough, then there is no way in which the hot parts, can exert pressure on the cold parts. And so the standard argument for the Denton limit doesn't hold. And indeed, if one plugs in the typical numbers in these common envelope systems, the inflow velocities of the gas are typically way higher than the diffusion velocity of the light, which means that light is indeed trapped and radiation pressure cannot hold accretion. Now, this leaves another problem, which is that if material just falls at an extremely high velocity, it will get extremely heated up, and then if this energy cannot go anywhere, the material will heat up, in principle, indefinitely. Now, this is not an equilibrium situation, and so to reach equilibrium, the key is that at some point the material gets so hot that the temperatures are of the order of 10 to the 10 Kelvin, which in natural units is of order an MeV. And then at these energies, the plasma starts producing positrons thermally that annihilate with electrons to produce neutrinos. These neutrinos, they can just freely escape, and they can carry away all the kinetic energy that the inflow gains by falling from infinity to the neutron star surface. And so it is really a combination of large inflow velocities that trap light, and hence this light cannot exert pressure on the outermost layers, and cooling by emitting neutrinos that allow extremely large accretion rates in this sort of common envelope neutron star systems. Now, here I just gave the hand-wavy physics picture. The devil is in the details. The mean uncertainty is the accretion rate that here I just estimated on very simple and hand-wavy terms. And on top of that, doing simulations is hard. So even though the basic picture has been mostly not understood since the 90s, the details are still tricky. So for example, when material falls onto a neutron star, it will typically have some non-zero impact parameters, so it will typically carry some angular momentum. And so to really fall onto the neutron star and get accreted, it will have to somehow dissipate the angular momentum. So this in principle could limit the accretion rate. On top of that, it's not really clear if 100% of this energy gained by the inflow is really dissipated by the neutrinos, or whether there are jets or other mechanisms that dissipate part of the energy. And on top of that, it's relatively simple mathematically and numerically to study the steady state stable scenario, but the dynamical details of how you start with a neutron star that is basically in vacuum to a neutron star that is inside the envelope and is accreting at extremely high rates are still not extremely well understood. So people are doing detailed simulation to get a better understanding of these questions, but still, I must say that recent three-dimensional simulations that include many of these effects still find that neutron stars inside giant stars in common envelope systems accrete at rates that violate the Denton limit by orders of magnitude. Typically, simulations find accretion rates of order 0.1 solar masses per year. And these extremely high accretion rates, in principle, are only possible because the system can cool down, can dissipate the energy that the inflow gains when falling onto a neutron star by emitting neutrinos. So the good thing of working in astrophysics is that one can show beautiful pictures. So this is a picture from one of these three-dimensional simulations that I was mentioning before, in particular from MacLeod and Ramirez Ruiz. And in the simulation, this white dot shows the neutron star. So this is the neutron star that is traveling inside the giant star, shown in the neutron star rest frame. So in neutron star rest frame, there's here a wind falling onto the neutron star. So these lines represent the velocity of the fluid, and the color represents the density of the fluid. So in the earliest stages of the simulation, up here in the top left corner, accretion is basically spherical symmetric, and everything is pretty simple. But then, as the simulation advances, There are turbulent phenomena, three-dimensional phenomena that create a sort of accretion spiral. And these phenomena tend to reduce the accretion rate from the naive estimation that I was mentioning before by a couple of orders of magnitude, but still they find that accretion should happen at super Eddington rates, which again, in principle imply neutrino emission. So once that we know the accretion rate, that as I was saying is the main uncertainty, one can easily estimate other properties of these events. So first of all, one can easily estimate the duration of these events because the rate at which material falls onto the neutron star, that is the accretion rate, m dot, tells you the rate at which the infall gains linear momentum, which, because of momentum conservation, tells you the rate at which the neutron star loses linear momentum. So this tells you the time scale after which the neutron star will lose all its linear momentum and just fall onto the companion, and then the process will end. So this gives durations of these events of order 1 month, 2 months, 3 months. Now, one can also estimate the rate at which these events happen in the Milky Way, and here the astrophysical uncertainties are huge. So partly because we have never seen one. So from X-ray binary catalogs, people have estimated that common envelope events involving neutron stars within the Milky Way should happen with a frequency of about 10 to the minus 2 or 1 events per century. So this is definitely not an extremely large rate. This is not a super common event. We are not going to see one tomorrow, and the day after tomorrow, and the day after. But it's also not once per Hubble time. This is not small enough so as to be completely hopeless. So I will talk more about the rate at the end of the talk. So wrapping up, this was most of the astrophysical summary. So understanding common envelope is key to understand the origin of many binary systems, including X-ray binaries, gravitational sources, and so on. However, we do not have direct and ambiguous observational windows because all the action is happening inside the envelope. However, super Eddington accretion, which has been hypothesized since the 90s and which recent simulations still find, would involve extremely high accretion rates lasting for about a month, where neutrinos again would play a key role because they are responsible for dissipating the energy gained by the inflow. So, how can we look for these events? Well, of course, because neutrinos would play a key role in these sort of events. So, what we did in our paper was to estimate the properties of the neutrino signal to see if this would be detectable or not. And again, here my main take-home message is that even though the astrophysical environment is very complicated, neutrinos play a fundamental role, which is to dissipate the kinetic energy that the inflow gains when falling from infinity to the neutron star surface. Hence, energy conservation arguments determine the main properties of the signal. So for example, one can estimate roughly the typical temperatures of the region of the plasma that is emitting neutrinos. And to do so, we can first estimate the rate at which this plasma gets heated up. So the energy per unit time and per unit volume that the plasma gets. So this energy comes because it is accelerated by the gravitational field of the neutron star. And so the kinetic energy gain is the potential energy loss. GMM over R, that's it. Now, since I want the energy per unit time that the plasma gains, I have to multiply not by the mass that falls onto the neutron star, but by the mass per unit time that falls into the neutron star, so the accretion rate m dot. Now, to get the energy per unit time per unit volume, I have to further divide by the typical volume in which this energy gets deposited. And here I have approximated this as a spherical shell of radius RNS over 2 at a distance or at the surface of the neutron star, at the distance of RNS. Now, this is just a very rough estimation. Let me make this clear. There are many order 1 factors here modifying the result. But as I will show in a second, I don't care about these order 1 factors. Now, since again neutrinos carry away this kinetic energy gained by the inflow, then I can equate, at least in equilibrium, this rate at which the inflow gains energy to the rate at which the system cools down by emitting neutrinos. Now, this is a weak interaction process, so it is suppressed by the Fermi constant squared. And because of dimensional analysis, And since this happens at very high temperatures, so there's no other relevant scale with units of energy, this goes as the ninth power of the plasma temperature. So this is the temperature of the plasma that is emitting neutrinos. And so by equating the rate at which the system gains energy to the rate at which the system can dissipate energy by emitting neutrinos, we can estimate the temperature of the region that emits neutrinos. And here the important dependency is this T to the 9, which means that the temperature depends on all the other inputs just as a power of 1 over 9, which means that order 1 corrections to the inflow heating or to the neutrino cooling rate will not dramatically change the temperature of the plasma, which in turn gives the typical energies of the neutrinos that are emitted. So this idea is shown here graphically. The vertical axis shows the rate at which the system cools down by emitting neutrinos as a function of the temperature of the plasma. So this green line is the exact weak interaction calculation. This is not dimensional analysis. This is the proper weak interaction calculation. And that, as I was saying before, goes roughly as the ninth power of temperature. Look at the huge vertical scale versus the relatively mild horizontal scale. Now, by equating this rate at which the system can cool down by emitting neutrinos to the rate at which the system gains kinetic energy, we can estimate the temperature of the region that is emitting neutrinos. And since this is a system in thermal equilibrium, one can get the average energy of the particles that emit neutrinos by multiplying this temperature by 3. And this gives us roughly the typical neutrino energies. And if you do the numbers, this is of the order of 4 MeV, which is large enough to be detectable. Now, once we know the typical neutrino energy, one can estimate the typical neutrino flux. So how many neutrinos per unit time, in this case, so what is the typical neutrino emission rate, how many neutrinos per unit time does this system emit? And to do so again, the basic idea is that neutrinos here play the key role of carrying away the energy gained by the inflow. And so to estimate the number of neutrinos per unit time, everything we have to do is to divide the energy that has to be dissipated per unit time by the average neutrino energy. That's it. So this energy per unit time is kinetic energy gain, so this is gravitational potential energy loss, Gm over R. And by plugging in numbers, we get typical neutrino emission rates of the order of 10 to the 50 neutrinos per second, which again is pretty large. And so if we place one of these objects within 10 kiloparsecs of the Earth, then the flux here at Earth should be of the order of 10 to the 4 neutrinos per square centimeter per second. Now, at these energies, the most efficient channel to detect neutrinos is inverse beta decay. So electron antineutrino plus proton goes to neutron plus positron. And so we multiply this flux times the cross-section for inverse beta decay times the number of protons in a detector like Super Kamiokande. We get that one of these bursts should produce about 100 events over a few months at a detector like Super Kamiokande. And so this event rate looks large enough to be detectable. So of course one has to be careful with backgrounds and efficiencies, but this at least looks promising enough to be worth a more detailed calculation. So everything that I was mentioning up to now were robust order of magnitude estimations, but order of magnitude estimations. So to get a more precise prediction, we sharpened these estimations via simulation. So basically, and this is my most technical slide, simulating the accretion inflow close to a neutron star is relatively simple. So the basic equations have been known for many decades, and they are relatively simple to implement, at least for simple scenarios. And so the main input that one needs is the rate at which material is getting to the neutron star. So that is harder to simulate, but what happens just at the neutron star is easier. So what we did was to take as an input the accretion rate that is predicted by one of these three-dimensional simulations. So this gives you the mass per unit time that falls onto the neutron star, and then once you have that, you can more or less easily simulate how that mass falls onto the neutron star, how it gets heated up, and how this leads to neutrino emission. So I don't want to enter the gory details, but we detail extensively how to predict the neutrino flux, and also to make future work easier, we have made our code publicly available. So in any case, after the calculation, we get this neutrino spectrum. So this is number of neutrinos per unit energy that are emitted over the entire duration of one of these events. In green is electron neutrinos, in orange is muon or tau neutrinos, and the electron neutrino flux is larger because these neutrinos are mostly produced via positron annihilation that mainly produces electron neutrinos. Now, as I was saying, this comes from simulation, but still this agrees very well with the order of magnitude estimations that I was mentioning before. So average energy is about 4 MeVs. Spectra that look more or less thermal. This is not because neutrinos are thermalized with each other. This is because neutrinos are produced in a plasma that is in thermal equilibrium. So they inherit thermal distributions. And also, if you integrate this curve and divide by the 3 months that I mentioned before, that these events last for more or less, you get a neutrino emission rate, which is of the order of 10 to the 50 neutrinos per second. So everything here agrees very well with the simple energy conservation estimations. So once we have the expected spectrum, we can run it through simplified detector simulations to understand what the signals would look like in different detectors. So starting from archival supercambiocante data, this the orange line is how the signal would look like for an event at a couple of kiloparsecs. In solid is for normal mass ordering, in dashed for inverted mass ordering. The rates or the flux is different because neutrinos undergo oscillations before leaving the entire system, and in particular oscillations in the envelope of the progenitor lead to flavor transformations that can modify the amount of electron antineutrinos here at Earth, which are the ones that you really detect. And this transition probability depends on the mass ordering. So for normal ordering, the rates are higher by a factor of 2 or a factor of 3 more or less. Now, in green here, I show backgrounds, and this gray bin at lower energies is a bin that we did not include in our analysis because, to our understanding, there are no publicly available collaboration estimated backgrounds at these low energies. But as you can see, there is a lot of signal in this energy bin, so unless the backgrounds here increase by a factor of a couple of hundred or more, then there could be more to gain by looking at this energy bin, and then the sensitivity would be better than what we claim. Now, here I say the word archival data because of 2 reasons. The first reason is that to our understanding, nobody has looked for transient months-long MeV neutrino signals. This means that in principle, there could be a signal hidden in archival data waiting for us to discover it. And the reason why it could be there and maybe we haven't seen it is because, to my understanding, all the data analysis extend over 1 year or a few years. And so if over a few years the signal stays the same, because this is integrated over the entire duration of the event, but then the backgrounds get multiplied by a factor of 10 or by a factor of 30, then as you see, the backgrounds completely swamp the signal. So you really need to search for months-long transient signals. And in principle, there could be a signal hidden in archival data for all the decades that Super K has been looking at the sky. Now, the other reason why I say archival data here is that Super K has become much better in detecting inverse beta decay relatively recently because they now have gadolinium in their detector that increases the efficiency to detect inverse beta decay. And so the fact that they have gadolinium means that the signal would look like this. So the detection efficiency is higher, so the number of events would be higher, and the backgrounds are comparable. I must say that this is not exactly how Super K looks like as of now, because this is for a publicly available data release that was for a smaller concentration of gadolinium than what they have as of now. So as of now, they have more gadolinium. So in principle, things should look more optimistic than what I will show. Now, another experiment that has a pretty good sensitivity to these signals is Juno. And this is because, very roughly speaking, Juno is as big as Super K, but it is filled with liquid scintillator and not with water. And this means that it has a higher efficiency to detect inverse beta decay. And so a signal in Juno would look like this here in orange, and you can compare the vertical scale. So as you can see, this is increased by a factor of by a factor of 10. So the number of events in Juno would be at least 10 times higher than in super K. So in principle, has a pretty good sensitivity to these sort of events. And finally, we also looked at how the Dune experiment would observe one of these events. And the idea is very simple. So in principle, Dune does not have hydrogen, so it does not have sensitivity to inverse vitality products. So Dune could detect one of these events by neutrino electron scattering. Now, neutrino electron scattering has a much lower cross-section than inverse decay, so you can see here that the event rates are much lower. However, neutrino electron scattering is directional. So by reconstructing it, you can pinpoint at where the source is. On the contrary, inverse beta decay is not directional, and so one could not, in principle, point out at where the common envelope source is located. Now, the fact that the cross-section is smaller means that we have to be extremely lucky and get one of these events relatively close to the Earth. But if we do, then Dune could, in principle, point out at the point in the sky in which this event is taking place. Now, once you know how the signal would look like in different detectors, you can estimate the maximum distance at which different detectors would be able to detect a common envelope event in neutrinos. And this is shown here in this plot. So the horizontal axis is distance, and the different vertical lines correspond to the maximum distance at which different detectors would detect one of these events. So for example, archival Super K data has a distance reach of about 5 kiloparsecs, more or less. So here to aid for the comparison, here there's a picture of our Milky Way. This is us, and with 5 kiloparsecs, you can cover this fraction of the Milky Way. Now, Super Kamiokande with low gadolinium, or most interestingly, Juno, could reach a distance of about 10 kiloparsecs, which is a large fraction of the Milky Way. It even includes the galactic center. And for Super Kamiokande with a large concentration of gadolinium, which is what we call here Super Kamiokande gadolinium optimistic, then the distance reached will be even higher. And if you fill hyper K with gadolinium, you cover basically the entire galaxy. And so to make a comparison for what does it mean to cover a few kiloparsecs, this black line shows the fraction of Milky Way stars within some given distance. And so as you see, archival Super K data could cover 10, 20% of the galaxy. Current low gadolinium Super K data could cover 30% for 40%. Juno could cover 70% more or less. And Super Kamiokande with a lot of gadolinium or Hyper Kamiokande with gadolinium would cover basically 100% of the galaxy. So down here, I show the sensitivity for neutrino electron scattering. And so here the numbers are not very good, but again, as I was saying before, if we are lucky enough so as to have one of these events within our nearby environment, then we could point out where the source is in the sky. So to give some context and some comparison to other astrophysical neutrino searches, there are many well-motivated searches for pre-supernova neutrinos. These are neutrinos that are emitted before a core collapse supernova explodes. And the distance reach of pre-supernova neutrinos, even if you use Juno, is a couple of kiloparsecs at most. And this is because pre-supernova neutrinos are pretty low in energy, so they are very hard to detect. So with this comparison, I am not saying, so let me make this clear, I am not saying that we should not look for pre-supernova neutrinos. Quite the opposite. There are very few astrophysical neutrino sources, so we have to look for all of them just in case we get lucky with one of them. On top of that, supernovae are in principle more common than common envelope, and so in part this compensates for the lower distance reach of pre-supernova neutrinos. What I wanted to say with this comparison is that common envelope is as good as or even better in terms of distance reach than other well-motivated astrophysical neutrino sources. So very bluntly speaking, if we look for pre-supernova neutrinos, why shouldn't we look for common envelope neutrinos? So in summary, neutron star common envelope systems, so systems in which a neutron star is swallowed by a giant star, are key to understand the origin of many binary systems. However, they have never been observed unambiguously, and that's partly because all the action is being hidden by the stellar envelope. However, it has been known since the 90s that if, as suggested by simple accretion theory and by more detailed simulation, accretion is indeed super Eddington, then the system cools down by emitting neutrinos. So what we have shown in our work is that an event within the Milky Way would produce detectable months-long MeV neutrino signals, thus making common envelope the third MeV astrophysical neutrino source after the Sun and supernovae. The downside is that this is a rare event. As I was saying, we're not going to see one tomorrow and the day after tomorrow. But this is not once per age of the universe, so the rate is high enough so as not to be hopeless. And indeed, the only way to guarantee not to see it is by not looking for it. So if you don't look for it, you are guaranteed not to see it. If you look for it, there is some chance, that is non-zero, that you may catch one of these events. So to give an idea and to give some quantitative comparison that is pretty fun, is that we have never detected neutrinos from a core collapse supernova in the Milky Way, because the supernova neutrinos that we detected 35 years ago came from a supernova in the Large Magellanic Cloud. And the core collapse supernova rate in the Large Magellanic Cloud is roughly once per millennia. And so still, even if the rate is once per millennia, after looking for a decade more or less, we observe one event. Again, this doesn't mean that you will see one event every time that you see, but it means that at these low event rates, everything that you can do is look for it and hope to get statistically lucky. So what would happen in case of a detection? What would we learn? Well, first of all, common envelope evolution would be an ambiguously established observationally for the first time. This is a statement that is hard to underestimate because, again, common envelope is key in astrophysics, but we don't have direct observational evidence for it. On top of that, super-Eddington accretion would be observationally established, and in this case, it would be interesting to look for other signals that people have proposed that are either electromagnetic or in gravitational waves, that even though they are slightly more ambiguous, one should, again, look for them, because in case we see one of these signals and we don't see the neutrinos, this means that there is something there going on that is inhibiting super-Eddington accretion, and this means that we have to modify our theoretical models and our understanding of these environments. Now, we think that we just scratched the surface of these processes. So from the astrophysics point of view, we really encourage the simulators of common envelope to take into account these neutrino emissions so as to provide sharper predictions on what the neutrino signal would look like, what would be the time profile, and what would we learn from it. It would also be interesting to understand what happens if accretion happens onto a white dwarf and not onto a neutron star, and this is just because white dwarfs are more common. The temperature of the plasma is probably not as hot, so probably the system would not cool down by emitting neutrinos, but still people claim that there could be some nuclear reactions going on the accretion inflow that in principle may also emit some neutrinos. That's something that we are looking at. From the experimental point of view, I think that's where most of the work is needed. So we really encourage experimental collaborations to carry out dedicated searches for these signals, including archival data, because in principle, there could be a signal hidden in archival data. So this signal is rare, but if you don't look for it, you are guaranteed not to see it. The only possibility to get lucky and catch one of these events is by looking for it. And also from the theory point of view, we didn't explore in detail with what sort of particle physics we would learn from this event, but in principle, neutrinos travel very large densities before exiting the system. So in principle, one could use these events to test for non-standard neutrino-matter interactions. On top of that, the system, this is key for all the calculations, the system cools down by emitting neutrinos. So if there are new particle physics processes that can dissipate energy without neutrinos, then this would definitely change the shape of the neutrino signal. And so to make this future work easier to carry out, we extensively detail how to predict the neutrino flux. So this is everything from my side. Thanks for your attention, and thanks for the invitation, and I am open for questions.
Thank you very much, Ivan. Are there any comments or questions? I see Segev has the hands up.
Yeah. Really nice talk, really interesting. Very much in line with your group's work, finding new stuff to look for. Your former group, I should say. Just a dumb question. Assume that we took the Super K data and did the archival search and didn't find anything. Do you already have an idea of what impact that might have on the rate of these kinds of common envelope systems in the Milky Way? Could we already reduce that sort of 10 to the minus 2 to 1 per century?
Yeah, so I guess the problem here is very similar to the problem you have with the standard core supernovae. That we have been looking for neutrinos from core collapse supernovae for a relatively short time, or their 40 years. So this means that probably the rate of core collapse supernovae in the Milky Way is less than 1 per 40 years, but there are better ways of astrophysically getting limits on this bound. So yeah, I doubt that we can learn a lot out, or we can improve a lot on this number, just because we haven't been looking for enough. So yeah, here it's a pity, but yeah, I think that what we will learn is that nothing has happened in the Milky Way in the last 10-20 years, but that's it.
Okay, thanks.
Any other comments or questions?
To summarize how we would look for this as an alert, if you're an experiment, you'd be watching your diffuse supernova background window and watching for a rate in that window
Exactly.
to go up over the course of a month.
Exactly.
Okay.
Exactly. The diffuse supernova search has very similar energies. This goes to slightly lower energies, but it's not a huge factor. So DSMB searches are typically at order 10, 15 MeVs. This extends to lower energies, but yeah, roughly speaking, that's what you do. You look in your DSMB energy range, and you look for months-long excess over backgrounds.
Okay. And it wouldn't be confused with pre-supernova neutrinos, which are of lower energy yet.
Exactly. On top of that, for pre-supernova, you have a core collapse supernova there after some time. But yeah, in case that you are using a similar window as a pre-supernova alert, the main difference would be in the energy.
But just I guess here, basically the bad point for this kind of detectors is that I think you're considering the background for instance, from reactors and the low energy background.
Yeah.
But from 10 to 20 MeV, where there's no background included, there will be a lot of IBD-like coincidences from neutral current atmospheric neutrinos.
Yeah, so very good point. We do take that into account, and in principle, the UNO collaboration has provided them. I think we took them from a dark matter search at these energies. So yeah, those backgrounds, we do take them into account. They are just down here. We don't show them because they are small. But yeah, I fully agree that the main, as in any DSMB search, the main background here at this 10-15 MeV range comes from atmospheric neutrino pressure. And
Okay.
yeah, and in principle, one good thing is that, and this links with the other question or comment, that one good thing is that in terms of energy range, in terms of background, this is very similar to the SNB. This is very similar to the diffuse supernova neutrino.
Yeah.
It's just shorter in time, which means that
Yeah, but this has on top that you can kill the background with the time window indeed.
yeah, exactly.
You
So
don't integrate over 10 years. Yeah.
exactly. And the good thing is that any technique that experiments develop to reduce the backgrounds for the SNB, which are very important, because anything that you gain is important, can also be applied to these sort of searches. So that's another reason why we really encourage experiments to look for it, because we think that the investment it takes in terms of characterizing the background and defining the search window and so on is very transferable to other searches, and you just have to look for shorter time scale windows.
I see also a hand from Jim.
On the pre-supernova neutrino, the typical energies are all right, a little bit lower than this. They're more like 2, 3, 4 MeV, because the processes are very similar, right? You just it's the same process that produces the pre-supernova neutrinos producing the neutrinos here. But in addition, in pre-supernova neutrinos, you have neutrinos from decays, and those can extend up to 10 or more MeV. So there are some higher energy pre-supernova neutrinos. And actually, Kelly Patton will talk about this next week for those of you who are in SNEWS. She told me that she will present something about her recent work. on the pre-supernova neutrinos.
Very interesting, yeah, very interesting comment. Yeah, definitely. Yes, I fully agree that this is the same process that produces pre-supernova neutrinos and essentially also supernova neutrinos in the accretion phase. Indeed, the order of magnitude estimations that I was mentioning before about the neutrino energy and flux, if you change the accretion rate from 1 solar mass per year to 1 solar mass per second, which is a supernova, you get a very good. So this is a huge difference in accretion rate, but if you plug in those numbers, you get a very good approximation for the typical energies of supernova neutrinos and for the typical fluxes. So yeah, then I agree that it's very important to distinguish this from. So to distinguish this from pre-supernova, I would say that the best way to distinguish it is a posteriori because pre-supernova comes with the supernova after that. But yeah, it's also important, I agree, to precisely characterize the properties of pre-supernova neutrinos and to see how far in energy they go to make sure that you can distinguish between both. Regarding potential neutrinos from decays and from nuclear decays, we did look at this in case of common envelope, but what happens basically is that the temperatures here are so large, of the order of 1 MeV, that all nuclear reactions are in thermal equilibrium. So the direct reaction and the inverse reaction happen at the same rate, and then the system enters thermal equilibrium and chemical equilibrium, and then you end up basically with hydrogen and helium that don't decay to produce neutrinos. So intuitively, and as somebody that hasn't not worked in nuclear physics, the way in which I understand this is that heavy nuclei are broken apart by all the high energy photons present in the system. So these are temperatures of other MeV that can easily break heavy nuclei.
If you're seeing pre-supernova neutrinos, then you'll very quickly learn that they're pre-supernova neutrinos within a couple of days, because you're going to get an explosion.
Exactly. So
Good. Any other comments or questions? Otherwise, let's thank Ivan again for this seminar, and we can give room to any other items to discuss before closing the meeting. Okay, so yeah, I think we can close the meeting here for today, and we will meet again next week for the signal
for the
prediction.
invitation, and yeah, if you want to know more or if you need anything, just let me know.
Thank you.
Bye bye.
Thanks.
Bye-bye.
Bye bye.